We were looking at this question related to a joint PMF where we first found the joint cumulative probability using this joint PMF. Then we looked at how can we find the conditional PMS for X and Y. And now finally want to do the last part where you want to see okay, are X and Y independent or not. So this is the last part we want to look at. Okay, are X and Y independent or not? Now for this, let's recall something. So let's recall two discrete random variables are independent. So two discrete, I'm writing DRV short for two discrete, short for discrete random variables. They are independent if and only if the following equivalent conditions hold. Sorry, if and only if, sorry, let's just write this properly. So we're first looking at in general what the conditions are, then we'll apply to this example if and only if the following equivalent conditions hold for all X and Y. Hold. This is a very important thing. So this thing for all X and Y is very important, right? What are the conditions? The conditions are that the probability X is X and Y is Y is equal to the probability X is X times the probability Y is Y. This means you can write the joint PMF as a product of the marginal PMS of X and Y, right? So this has to be true for every single value of X and Y. Then the second is that probability X is X given Y is Y has to be equal to the probability X is X. Right, and this is again has to be true for every possible value of X and Y. Then probability of Y is Y given X is X has to be equal to the probability Y is Y. So basically the conditional PMFs have to be equal to the marginal PMFs. Right, because obviously if independent, then given Y is equal to Y should make no difference when you're finding probability X is X. Similarly, when you're finding probability Y is equal to Y, then given X is equal to X should not make any difference if independent. And all of these have to be true for every single value of X and Y. Now, something that we do want to focus over here is the term equivalent. Right, let's focus on this. Since all the conditions, these conditions are equivalent, they all imply one another. Since all the conditions imply one another, they're equivalent. So proving one is enough, right? So you don't have to prove each one of them to show the independent. You can just prove one. Imply one another. So proving any one condition is enough, right? So this is important. If you want to show the independent, you can just prove any one. Proving any one condition is enough. But there is a but here. It's enough to show they're independent. But you need to prove it for every single value of X and Y, right? So this is important because it says that holds for all X and Y, right? But make sure to prove for all X and Y. So if you want to show the independent, you can choose to prove any one condition, but that condition has to be proven for every value that X and Y take. But make sure to prove for all X and Y. If we show any one condition, now this is how we can prove they're independent, but if we show any one condition is not true, again, you just need to show one condition is not true. And the good thing here is, if we show any one condition is not true, even for a single value of X and Y. So here we just need to show that one of the conditions is not true for a single value of X and Y if you want to show they're not independent. Even for a single value of X and Y, we have shown X and Y are not independent. We have shown X and Y are not independent. So the idea is that if you want to prove, you need to prove any one of these conditions for every possible value of X and Y. But if you want to show, if you are able to show that any one of these conditions is not true, even for a single value of X and Y, then you've essentially shown they're not independent. Because for them to be independent, it had to be true for every possible value of X and Y. So if it's not true even for a single value of X and Y, it obviously can't be true for every possible value and they're not independent. So proving they're not independent is a lot easier because we just need to show that this condition does not hold true for any one value of X and Y. But proving they're independent is harder because you need to show any one of these conditions is true for every possible value that X and Y take. Now let's apply it to this example. Now, since in parts B and C, we already found the conditional PMS, right? So in parts B and C, we already found the conditional PMS of X and Y. Since in parts B and C, we already found the conditional PMF of x and y. So let's use that. Right? We've already found it, so we can use that condition because we already have those. They're conditional PMFs. We already found conditional PMF of x and y. So let's use that, right? We already have them. We could use condition one is where we show probability x is x and y is y equal to probability x is x times probability y is equal to y. We can use this condition as well and work with this. But obviously we have already found the conditional PMF, so we can use those as well. We just have to either show any one condition is true for every possible value of x and y to show they are independent, or we need to show that any one condition is not true for even single value of x and y to show they're not independent. So we can work with any condition. Let's just use the conditional PMF one because you just found those conditional PMFs. So let's use that. So now from part B, we have found from part B, when we found the conditional PMF for y given x is equal to 0, we found in part B probability y is 3 given x is equal to 0 is 0.47. Let's check. Now this is for one value of x and y. Now this is for the pair of values of x and y where x is 0 and y is 3, right? So this pair. Right, so we're looking at this pair. So remember, even if right, so here we're checking this for right now just one pair of x and y, x is 0 and y is 3. Now let's check, is probability y is equal to 3 given x is equal to 0 is equal to probability y is equal to 3, right? So we need to check this. Let's check, are they equal? Right? If they are equal, then that doesn't prove the independent, right? Because you would have to check it for every pair of x and y, right? Like you would check it for y is 3, x is 0, y is 3, x is 1, y is 3, x is 2. Then you would check it for y is 4, x is 0, y is 4, x is 1, y is 4, x is 2. So you'd have to check it for every single pair that you have of x and y, like the condition, right? But if we show that this is not true, then we'll be sure they're not independent because the condition is not true for every x and y, right? So let's see what probability y is equal to 3 is. Right, let's check, is it equal? Now probability y is equal to 3. So we know to find, let's just erase this for a second. So we know to find probability y is equal to 3. You know, to find any probability using the joint PMF, we can just sum up the joint PMF over those values of x and y. So to find probability y is equal to 3, sum up the joint PMF over all those values. Y is 3 regardless of what x is. Values where y is 3 regardless of what x is, right? So y is 3 is over, sorry, y is equal to 3 is over here. So this is y is equal to 3. So we have to just sum up the joint PMF over all those values where y is 3 regardless of what x is, right? So it's this value, it's this value, and it's this value, right? So it's basically the row corresponding to y is equal to 3. We have to sum up the joint PMF over all these values where y is 3 regardless of whatever x is, right? So it would be this value, this value, and this value. So probability y is 3 is 0. So it's the probability y is 3 and x is 0, which is 0.09. Probability y is 3 and x is 1, which is 0.14. Plus probability y is 3 and x is 2, 0.07. So this turns out to be 0.3. Now probability y is 3 given x is equal to 0, 0.47. But probability y is 3 is 0.3. Since probability y is 3 given x is equal to 0 is not equal to probability y is 3, x and y are not independent. Right, so basically, remember, like we said, to prove they're not independent, you just have to show any one condition is not true for any one value of x and y. Here we're shown it's not true for the pair x is equal to 0 and y is 3. But now if it had turned out that probability y is 3 given x is equal to 0 was equal to probability y is 3, if that was the case, that would not have proved they're independent, right? So just this is something to note, that if it had turned out to be the case that probability y is 3 given x is equal to 0 had come out equal to probability, assume it had come out equal. Here it wasn't, so we said they're not independent. Had come out equal to probability y is equal to 3, that would not have proved they're independent, right? That would not have proven they're independent. To prove independence, you need to show that probability y is y given x is equal to x is the probability, this was the conditioner for all x and y. So first you would do probability, you would show the probability y is 3 given x is equal to 0 is true. Then you would have shown it is true, that then you would have done it for y4, probability y is 4 given x is equal to 0 is probability y is 4. Then you would have had to show probability y is 4 given x is equal to 0 is probability y is equal to 5 given x is equal to 0 is probability y is equal to 5. Then you would have had to show the probability y is 3 given x is equal to 1 is probability y is equal to 3. Probability y is 4 given x is equal to 1 is probability y is 4. Then you would have had to show probability y is 5 given x is equal to 1 is probability y is 5. Then you would have had to show probability y is equal to 3 given x is equal to 2 is probability y is equal to 3. And then you would have had to show probability y is equal to 4 given x is equal to 2 is probability y is equal to 4. And then probability y is 5 given x is equal to 2 is probability y is equal to 5. To show independence, you have to prove any one of these conditions for every possible pair of value that x and y can take, right? So we have to show it for every single value of x and y. But if we are able to show that any one of these conditions is not true for even a single value of x and y, then we've essentially shown they're not independent. So proving not independent is a lot easier, because over here we just showed, okay, probability y is 3 given x is equal to 0 is not equal to probability y is equal to 3, which meant they were not independent. Right? So this was a lot simpler, because see, to be independent, it has to be true for every possible value of x and y. So if it's not true for even a single value, they're not independent. So proving not independence is a lot easier than proving independence, because when you're proving independence, you need to make sure you show it for every possible value of x and y. So you have to work with every pair of value of x and y in a joint PMF.